This media was gratuitously produced by Clear Contributions Audio Video. The intellectual property contained within belongs to Dr. Barbara Van Kyken. Clear Contributions. Let's have clarity.
So I'm going to pound this chapter and the following two really hard because these are really, really important ones. Let's see, your test will cover nomenclature and reactions of carbonyl compounds. So this one's going to cover two chapters. Okay, and you see the learning objectives there, how to classify things. You have to classify them first before you can name them because the functional group ending will be dependent on what class of molecule it is, how to name a carboxylic acid, and then how to name all the other types. The reason why those are split out is because quite often the name for the other types is based on the name for the carboxylic acid, and then how to name more than one functional group. So first, since we're talking about carbonyl compounds and such, you probably want to know what a carbonyl group is. That's any time that you have a carbon with a double bond to oxygen. Usually you're going to have carbon groups attached to one side, or maybe a hydrogen. And then the other side, what's attached to the other side, that's what's fitting it into different kind of categories. You'll alternatively see an acyl to describe, they'll say like an acyl halide or an acyl group of a fatty acid or something like that. That's the same thing, it's just that you're talking about something that has carbons attached to it, which is described by the R. So I'm going to use that structure for the acyl group and show you what else is attached on the other side. Okay, so for a carboxylic acid, that one is kind of like what I've been saying, like euphemistically, is a coup group. It's where you have the carbonyl carbon, C with a double bond to O, and then you also have an OH on there. So that one's going to look like this. Do you want me to airdrop you, Josh, or somebody there want to airdrop him?
Yeah,
You've got him? Okay. An acyl halide, halogen, fluorine, chlorine, bromine, iodine, any of those. And so I'm going to diagram that out as an X to represent a halogen. Okay, then we also have acid anhydride. So an is without, hydride is without water. So on the right-hand side, I'm going to show you kind of how that name is derived, and then on the left-hand side, I'll show you what the structure actually looks like. Oops. It's like you have two carboxylic acids, nose to nose. Like that. And you remove water, H2O. So if I take out the two hydrogens and one oxygen and join those like that, that's what the acid anhydride looks like. Acid anhydrides are not found very much biologically because they're pretty reactive. Same thing with acyl halides, but they would be found, for instance, in a lab. Do you remember from last semester what an ether is?
There's an alcohol. There's an oxygen with two different things in there.
You have oxygen with something on ether side. Remember? The carbon's on ether side, yeah? Okay, so this is going to make you a little bit crazy. Ether and ester sound so similar, right? So at least it gives you a clue to the structure, but you got to keep it separated. And if you're struggling with it, don't feel bad, because I'm always going, ester. Because I have a hard time, they jumble in my head a little bit. And ester is the exact same thing, except the carbon on one side has a double bond oxygen. In other words, it has a carbonyl group. Carbonyl carbon as opposed to just a plain old run-of-the-mill carbon.
Ester and neal got together and had a kid, things like that.
Okay. And you remember from last semester, amine? It's where you have a nitrogen attached. And the nitrogen could have any number of carbons attached to it. Could be a primary, secondary, or tertiary amine. And amide, same issue as ester and ether. Amide and amine, they sound real similar. That means they're very similar structure. And amide has a carbonyl carbon on one side, though. Kind of sandwiched in there. And once again, the nitrogen could have any number of carbon groups attached to it. Well, as long as that number is between 0 and 2. A lactone is a cyclic ester. So you have your carbonyl carbon like that, and it has an oxygen attached to the carbonyl carbon. And then you know how you normally would have had some kind of R group there, some carbon group, and you would have had a carbon group over here. We're just going to put them together. It could be any number of members in the ring. 3 and 4 membered rings are going to be a lot more rare, though, because there's a lot of angle strain there. And more than 6 is also very rare because it's hard for the ends to find each other and connect together once you get a big chain. So usually you're going to see 5 or 6 membered rings. But an important 4-membered ring that you're going to see if you take like a med chem class or pharmacology or anything, you're going to learn about penicillin having a beta-lactam ring. It's a 4-membered lactam ring. And a lactam is a cyclic amide. So it's the same difference, it's just that it has a nitrogen as part of the ring. And then ketone, like for instance, you've heard of ketone bodies. That's where you have a carbon group on either side of the carbonyl carbon. Acetone is the simplest ketone. It just has a CH3 group on either side. And I think that I just borrow trouble when I show you this, but I'll show you why. This almost looks like, no, I don't want to do that. It almost looks like a keyhole, huh? But then once I say that, then everybody spells it K-E-Y-T-O-N-E. So I'm just asking for trouble there. And then an aldehyde is where you have a hydrogen on at least one side of the carbonyl carbon. The simplest aldehyde, you can have hydrogens on both sides.
Is R always symbolizing a carbon group?
Yeah, and it can loosely be used to describe a hydrogen alternatively, but generally it means carbons. Okay, and then the last one, nitrile. This doesn't have a carbonyl group on it, but it kind of reacts similarly, and so it's usually thrown into chapters here. A nitrile group is where you have a triple bond to nitrogen. For biology and chemistry, as I said, you're not going to see many acid anhydrides or acyl halides, but you will see a lot of carboxylic acids. Those are fatty acids, for instance. You'll see an amide as the peptide bond. That's the peptide bond between the carbonyl carbon and the nitrogen. Esters, phospholipids, triglycerides, yeah, all kinds of stuff like that. And ketones and aldehydes. So I guess what I'm saying is if you want to understand what's going on in biochemistry so you can just kind of reason it out instead of brute force memorizing everything, this will help you. Yep.
So is in the cell always going to be a cell, right? A cell is always going to be a carbonyl.
Yeah.
So all cells are carbonyls, not all are carbonyls. Okay, it's like the first 4, 5, or 6 we learned are both, but the ring structures are carbonyl only. I guess which ones are only carbonyls? I guess. Okay.
I think that you could say that all of them have an acyl group or a carbonyl carbon or carbonyl oxygen. They all have carbon and a carbonyl group. Yeah, so, and I'm sorry, I'm throwing things around. So although that's a carbonyl group, quite often they'll talk about the carbonyl carbon or the carbonyl oxygen to refer to something. Some feature when you're doing reactions. Okay, so before you can even name anything, you have to be able to recognize what functional groups are present. And I've thrown in some that have multiple functional groups and everything just because I want you to be able to distinguish between a carbonyl group and something where you have a carbonyl carbon and something else there present at the same time. So try to highlight what your functional groups are and the parent hydrocarbon, the substituents. So remember the functional group was in red and the backbone, the basis is blue, and the substituents were green. And then once you've got the functional groups labeled, or highlighted, I mean, see if you can identify what kind they are. Write a label for them. It's an acyl halide or whatever. I'll let you work on A for just a minute and then I'll show you what I mean before you practice the rest of the page.
So a question. Let's ask, how can you tell the difference between a ketone group and a carbonyl group?
A carbonyl group is present in all of these.
Right.
Because it's carbon double bond oxygen. A ketone is where the carbonyl group has a carbon attached on either side.
Oh.
All right, so see the first one you have 2 functional groups present. I was trying to make sure I could help you distinguish between that and a carboxylic acid. right? Because for it to be a carboxylic acid, the OH would have to be attached to the carbonyl compound. Notice that on the previous page, everything you're talking about what's attached to the carbonyl compound specifically. So this one you have a carbonyl compound, and then it has a carbon on either side. So that's a ketone. The OH is just another functional group that's present there.
So an alcohol and a hydroxide, is that same thing, different name?
Mm-hmm.
Okay.
So now when you see the oxygen with the double bond, it'll always be
It's a carbonyl group, and then what else? Yeah.
like a functional group?
Yeah, it's a functional group, yeah. And then it has something attached to either side. Look at what that thing that is that's attached to it. I don't know if this, maybe this will help you first. So you're looking at the carbonyl carbon and what's attached to it. So you have a hydrogen on one side and an oxygen on the other. The hydrogen, you could think of that as kind of part of an R group. Okay, so you have an oxygen present on the other side. So if you come back here, there are two cases where you have, no, three cases, sorry, where you have an oxygen attached to a carbonyl carbon. A carboxylic acid, that oxygen is an OH. An acid anhydride, that's an oxygen with a carbonyl group. And an ester, which is an oxygen with some carbon attached to it. So this is an oxygen with a carbon group attached to it, so it's an ester.
So does that make the whole molecule ester? I guess we're not naming things.
Yeah, we're not naming things quite yet. And I've been struggling with how you can highlight stuff, so I figured, well, it's the oxygen plus whatever's attached to the carbon is what's defining the functional group. So I don't know, I've been kind of like, put those two together, kind of thing to highlight it. And why did you go away? The reason I am struggling with how to highlight it is because the carbon is part of the parent hydrocarbon. And so that's why I'm not highlighting it as part of the functional group.
That's
But
the
it is part of the
parent
functional group,
hydrocarbon is
too.
how you determine what functional group it is.
Yeah,
The oxygen is just like the indicator. You're like, oh, oxygen, there is a functional group present, but the rest of it is how you name
yep, uh-huh.
So would B also be an aldehyde because you have one side is hydrogen, or does like the ester override the aldehyde?
The ester overrides the aldehyde.
it.
The aldehyde is if you
Up
have
most of it.
a hydrogen or carbon on one side and a hydrogen on the other,
Okay,
specifically.
so you have to have a carbon group on one side for the aldehyde.
It says that it's checked. Well, I guess that gives you a chance to work down the rest of the page while I mess with this. Okay, so this one, here's your carbonyl group, and you're looking what's attached on either side. So you have a carbon and a hydrogen. Okay, so match that up. What kind of group is that?
Alkyne.
It's an aldehyde. For it to be a ketone specifically, you have to have carbon attached on either side. So this, the functional group is the aldehyde, that part there. This is your parent hydrocarbon right here. And then you have a substituent here. Okay, and then you have a propane and you have a bromo group.
So for the acyl halide, this one wouldn't count because the carbonyl carbon is not directly attached to the bromine?
Exactly.
It has to be direct, okay.
Directly attached to the carbonyl. Okay. Here is carbonyl carbon here and a carbonyl carbon here.
Ketone, ketone.
Ketone, ketone. right? That's not an acid anhydride. You'd have to have an oxygen in between them. So you're just looking at, I've got a carbon group here and a carbon group here, so this part here is a ketone. Right, and then the same thing over here, carbon group, so that's a ketone. And you won't have to garbage it up with all the yellow highlighting probably once you get going, but just to help you see right now. So that means that this is a functional group here, and it includes the carbons, but the carbons are also part of the parent hydrocarbon. So that's why I'm struggling a little bit with how you can diagram it out to picture it. So if you've got suggestions, let me know. So here's the ketone. You have an oxygen attached to it. There's 3 cases where you'd have an oxygen attached: carboxylic acid, acid anhydride, or an ester. Yeah, ester. If it was carboxylic acid, you have a hydrogen attached to the oxygen. If it was an acid anhydride, you'd have a carbonyl group attached to the oxygen. This has a just plain carbon attached to it, so that's an ester. So your functional groups are there. Your parent hydrocarbon has to include the functional group, so it has to include the carbonyl carbon. Even if it's not the longest carbon chain, it's just like before. It has to include the carbonyl carbon. And you can't skip through a non-carbon atom. So, whoops, that's not what I wanted to do. So this is going to be your substituent.
Does the substituent include the oxygen?
No. Good question.
So then how do we name it again? Oh, we're not there yet.
So excited, aren't you? Yeah, maybe tomorrow.
Okay.
Yeah. But the name would be based on ethane. All right. Here's your carbonyl group. And you're trying to figure out what's attached to it. You have a nitrogen on one side. So it is a and amide. Okay. All right, then the parent hydrocarbon has to include the carbonyl carbon. Everything else is a substituent.
Why are you highlighting the oxygen with the nitrogen and the red? Oh,
Because it's like a functional group.
Okay, so you do the yellow first and then the
Well, yeah, and I don't know if, I don't, to tell you the truth, I've been playing around with different things to help you see it, and I'm not sure I've settled on something really great yet.
I like that.
No,
Yeah.
I like it. I just wanted
Okay.
to, okay, now I remember it's red is functional, yeah.
Okay. All right. Here's your carbonyl carbon. You have a carbon attached to it and a halogen attached directly to it. So that is a acyl halide. You also have an alcohol group there, but it's not part of that carbonyl functional group because it's not directly attached. And you have the parent hydrocarbon. I don't think I labeled anything last time. Am I? So, oh yeah, so that's right. I remember now when I was creating this. I wanted to give you a little bit of extra workout. Sorry. Going back to F, what's the big functional, or big substituent in green there. Isopentyl. You remember! That's terrific. It took less than 5 minutes to come up with that. Yay!
We have a
I'm sorry, I've been really lazy. I've been so excited about teaching you about the functional groups, I haven't been labeling anything as we go. There we go. All right, and then the last one here. We have 2 carbonyl groups. They both have an oxygen in between, so that is acid anhydride.
Is it acid anhydride?
Yeah, or sometimes they just say anhydride. This one has 2 parent hydrocarbons because you have 2 carbonyl groups that are. It's like you put 2 carboxylic acids together, so you name both of the carboxylic acids that were joined together. So this is going to be the only case I can think of this year where your parent hydrocarbon, you have 2 parent hydrocarbons and on either side of something. Okay, so it's just a little practice. Okay, and then this is your other flashcard thing. You got to get this down, and once you get both of those flashcarded and kind of in your head, we can work a little easier with naming stuff. You know how last semester with common name, you could only describe certain structures because there were no position numbers, and it switched up what the priority was for what you're basing the name off of. This, however, when you're naming carbonyl compounds in common name, it's very similar to IUPAC, where you are identifying a root structure and then you can talk about substituents off of it in different locations. So it's a little bit different approach from last semester's common name. The common name for any of these compounds is based on the common name for the carboxylic acid. And so you're going to have to just memorize these. When you get into biochemistry and you start getting carboxylic acids with even longer carbon chains, you're going to be also memorizing the common names for those, and that will be stearic acid, linoleic acid, linolenic acid, and all of those. But for organic chemistry, we're just going up to 6 carbons. The first common name, if you only have 1 carbon in the carboxylic acid, this is formic acid. And you probably can already see down the road that when we name a formic acid derivative that's actually an aldehyde, then it'll become formaldehyde. Ah. And some of these come up, get their name from really weird associations. Like I think formic acid was originally discovered in ants, and ants have a genus or species name that has something with form or whatever. Anyway, it looks like these don't have any reason for being, but they do. All right. The common name for the next one is acetic acid. You learned acetic acid, well, I attempted to teach you acetic acid in general chemistry where you had the HC2, H3, O2. This is just it drawn out now for you. 3 carbons, the common name is propionic acid. That sounds a little bit like propane, right? And the common name for 4 carbons is butyric acid. That sounds a little like butane. that's going to work for you and against you in a minute, you'll see. I can't remember for sure, so don't quote me, but I think butyric acid comes from some kind of fatty acid that's present sometimes in butter or makes it taste rancid. I'll have to look up my random factoids. All right, the Roman numeral for 5 is V. Give me a V for valeric acid. I'm stretching here, but that one is hard to keep the number in your head, so. And then 6, I've got nothing for you. It's caproic acid. What do you notice about the endings every time?
It's acid.
Acid and ic acid. And so if you have a benzene ring that's a carboxylic acid, what do you think it is?
Benzoic.
Benzoic. Okay, notice I went through all common name, just because that's just memorize it. With the IUPAC, there's a pattern to it, and so that's why I wanted to do that as all one grouping. You name it based on the name of the parent hydrocarbon, like for instance methane, ethane, propane, butane, pentane, hexane, and you change the ending to oic acid. So IUPAC. And that's kind of like, you know, last semester we had if it's an alcohol, change the ending to OL. If it's an amine, then change it to amine. You had to know what a functional group ending was. For carboxylic acids, the ending is oic acid. And then to keep from having 2 vowels together, you usually drop the E from the parent hydrocarbon name. So you have a parent hydrocarbon that's methane. Change the ending to oic acid, methanoic acid. And now that you see the pattern, you can probably go down most of the rest of the page, except for that stupid benzene. Oh, look at that. Propionic acid and propanoic acid. Yeah, stinks to be you. So that's a case where I said it kind of works for you and against you that they're so similar. You can remember how many carbons there are. It's just sometimes you're sitting there going, which one is the common name? So if you know how to create the common name, that might help keep it straight a little bit for you. Oh, butyric and butanoic. So it really is all one word. I'm just doing it this way so that you can see how I got there, but it would be pentanoic. It's all one word. Okay, all right. The IUPAC name for these just make me really bitter. What is that? I don't know. I don't get it, but it doesn't follow the same pattern. With cyclic compounds, it's not going to follow that pattern of just put an oic acid on the end of it. All right, so I know that you have way too much information to be able to work with this right now, but I just want to show you real quickly how to put it together, and we're going to work on this a lot more tomorrow. Last semester, I told you, look for the functional group, the parent hydrocarbon, and the substituent, and highlight those. That's identify everything. And then in the second step, you wrote everything. Substituent, parent hydrocarbon, functional group. Going to be the same thing here. Then step 3, if you have more than one of something, say how many with di, tri, tetra, but don't alphabetize by that. Step 4, number, and say where everything is. And then step 5 is describe the stereochemistry. For common name, it's going to be the same exact kinds of steps where you identify everything and then write the name. The name is always going to be based on the carboxylic acid, and I'll go over this in more careful detail tomorrow. And then step 3, say how many, and step 4, say where, but you don't use numbers in common name. You use alpha, beta, gamma, delta. You don't start with the carbonyl compound. There's a lot of differences there with the common name that we got to sort out. But I just want to show you just real quickly how to apply this on page 11. And I know you're going to have to go to your cheat sheet, but all right. What kind of functional groups or groups do you have here? There's your carbonyl compound. I don't see any other functional groups on that part of it. So what kind of carbonyl compound is this? Yeah, I have an acyl halide because you have a halogen there. Okay, so that combination together makes up your functional group. After you've identified the functional groups, figure out your parent hydrocarbon because it has to be the longest continuous carbon chain that includes the functional group. And then figure out your substituents. Okay. All right, then put your substituents in alphabetical order, and that's going to be what? I should have highlighted this instead, sorry. I'll do it real quick while you're thinking. Bromomethyl, okay? I don't know, do we have 6? Probably. Yep. Bromo, methyl, hexane. Okay, and this is where you don't quite know yet, but this is an acyl halide. Specifically, it's an acyl chloride, because chlorine is the halide. So you use YL chloride as your ending. Okay, and you'll learn these tomorrow. We'll do it tomorrow. Don't freak out at me. And we'll drop the E just because then you'd have 2 vowels together otherwise. Do you have more than one of anything? No? Okay, so now the next step is you want to say where everything is, and you number each direction, giving the lowest number possible to the carbon directly attached to the functional group, remember? So this is happy because it's always going to be the number 1 here. You don't have to struggle with numbering like you did last semester. Okay, and you write the numbers out front. 3 bromo, 4 methyl, hexanyl chloride, sorry.
Wrong way around. 4-bromo.
Did I get it? Oh, bother. 4-bromo, 3-methyl hexanyl chloride. This time you don't have to put the number for the functional group because it has to be on the end because you have 3 bonds that just use up the functional group. So just like last semester, if the position was defined, like if it was part of a ring and everything, you didn't have to put a number, same thing here. All right, so make flashcards tonight, get that stuff down. Once you get all this stuff memorized, you're gonna be in a lot better shape.